It's very interesting, I think, that in our brains we have about 100,000 million neurons, all interconnected, giving us some consciousness. Interestingly enough, there's about 100,000 million stars in our galaxy, and we think that most of them have planets, and even if only 1% have life, that's still 1,000 million planets with life in our galaxy. If they do, we don't know. We know of only one, but we think we'll find out soon in our kids' lifetimes whether there's life on other planets around other stars, because we're finding ways of finding out what the atmospheres are like there and so on and so forth. Then, in the visible universe, which is perhaps only a small part of the whole universe, there's about 100,000 million galaxies. How do we know that? We have first the Hubble, now the James Webb, staring at a very small part of the sky and counting galaxies by the million there, but it's a tiny part, so you make the whole, over the whole sky, you figure out that in our visible part of the universe, something like 100,000 million galaxies. And maybe there are hundreds of thousands of millions of universes out there, which is a whole different concept. We used to think this was the world, Earth was the world, one. Now, okay, then we found planets. We thought, well, there's maybe 8 planets around the sun, and that's it. Then, now we know that there's actually something like 100,000 million planets in our galaxy alone, Milky Way galaxy alone. And here's a picture of the Milky Way galaxy. I hope you have all been able to see the Milky Way with your eyes. Anybody who's not seen the Milky Way with their naked eyes? It's not so easy in cities anymore. When I was a kid, I could go outside my door, not far from London, and see the Milky Way and the Andromeda galaxy, it's another galaxy, with my eyes. And unfortunately here, the sky is not so dark and clear, but get a chance to go to a place with the dark skies, do it. I've done it in Greece, in Argentina, and lying on the ground and seeing the sky is just an amazing experience there. In fact, the southern hemisphere is even better. But here, you see, with your eyes, thousands of stars, if you're on a good night, and you also see a lot of dark. The dark is important, actually. Why is the sky dark at night? Or anytime? So, have you heard of Olbers' paradox? No. So this was way back in the 18th century. Olbers wondered why the sky was dark between the stars. He said, look at the surface of the sun. The sun is about half a degree across, and it's a very bright surface, so you don't look at it, even during a partial eclipse. Look at it with your naked eyes when you've got a total eclipse, like I did last Monday. That was great. But he said, supposing the sun was twice as far away, then the surface brightness would be the same. It would look a quarter the size and be a quarter as bright, but the amount of light per square little piece of angle would be the same. So he said, so the further away the star is, take the sun further and further away, the surface brightness will still be the same. He said, supposing the universe is infinitely big and static, then in every direction you look, your eyes would hit a star. The light would be, the whole sky was as bright as the surface of the sun. It's dark. So that was considered a paradox. It's not really a paradox, but it's an observation. The sky is dark at night between the stars. So either the universe is not static or it's not infinite. It doesn't have infinite time. Now we know both of those things are true. The universe is expanding, it's not static, and also it's not infinite, I think. I believe it's not infinite. So that explains sort of why the sky is dark at night between the stars. Anyway, it's beautiful, so we should try and avoid too much light pollution and get where you can. So here's a picture from okay, so on the left you see a picture of the full moon. That's just to show the size of the full moon. And if you can see, I think I have a little square at about 7 o'clock. And that was where the Hubble looked in that square, and there are no stars in our galaxy. Looking between the stars, so looking out beyond the galaxy, and taking a long exposure, about 12 hours at the Hubble Space Telescope, and then seeing that even in that tiny square, there's lots and lots of objects, and they're all galaxies pretty well. So you can imagine in that square is such a small part of the whole sky, you count up, it must be about 100,000 million galaxies. Now that picture is a different one. It's from the James Webb, which is better, sees further. And every object in that picture is a galaxy or something even a bit weirder than a galaxy. Could be a quasar or something like that, because a quasar is one star that, where it explodes, becomes brighter than the galaxy even. So there, that's, but the universe was much younger here, because we're seeing those galaxies as from a distance of about 13 billion light years away. The light's been coming to us for 13 billion years. You know, it started out before there was the planet Earth. Planet Earth's about 4 billion years old. Life started fairly soon afterwards and didn't develop for a long time. We don't understand exactly how life started on Earth, but it could start on most planets that have conditions right, like water. And that may be only 1% of the planets. But if the conditions are right, like water and land and so on, and maybe life gets started on those. So we're now seeing back to the very beginning of... Now here's a brilliant picture. The one on the left is a picture of Earth. Can you see a little tiny dot in the... Those bands, they're just optical effects, reflections off mirrors and so on, but there's an arrow pointing to a little dot there, which is a pale blue dot. And this is a brilliant idea of Carl Sagan, because the Voyager spacecraft that we sent off, and it's gone beyond Pluto. And here he said, let's turn the camera around and point it down to Earth. Because, what are you doing that for? You know, we should do that. And he did that. It's the most iconic picture because it sees Earth as one pixel on that picture. And he's very eloquent. He says, all of us, all our wars and so on, all our life is on that pale blue dot. And when that was published, we hadn't yet discovered planets around other stars. That was 2 or 3 years before we started finding planets around other stars. But so now this, yesterday I checked the distance of this Voyager spacecraft. It's gone way outside the solar system. And you can read there, it's about 14 billion miles away. Its speed is 38,000 miles per hour. But the time to get to the nearest star at that speed would be about 5,000 years. So if you think that spacecraft and planets, even from the nearest star, which is about 4.5 light years away, take 5,000 years to get there at that speed, you begin to realize that probably we're not being visited by alien spacecraft from other planets, even if there's life there. There are more things in heaven and earth, Horatio, than I dreamt of in your philosophy. So, life. Here's a nice bit of the tree of life on Earth. And it's, you can see many of these pictures. So it seems that, well, Darwin had the idea, and it's now accepted by scientists, that life on Earth started not long after the Earth was formed, more than 3.5 billion years ago, when the first molecule was able to reproduce itself or make a template. So, you know, DNA, complex molecule. Interestingly, it's based on 4 elements: carbon, nitrogen, oxygen, hydrogen, plus a bit of phosphorus, but mainly those 4, HCNO. I find it fascinating that those are exactly the 4 elements that generate energy in stars, in the center of stars. HCNO, it's a cycle, they fusing hydrogen to helium. Carbon, nitrogen, oxygen are used as catalysts in that reaction. Isn't it interesting? The same 4 elements out of the 100 we've got are responsible for starlight, and the sun has also a different reaction, but still hydrogen burning into helium. and they're responsible for life. So if there was no hydrogen or carbon in the universe, no carbon, let's say. Now, carbon is the one element out of 100 that allows really complex molecules to exist. The one out of 100. If that silicon is similar, but can make silicon hydrides, but it doesn't make really complex molecules. If that carbon didn't exist, then it's hard to think how life, as we know it, would exist. Same thing, hydrogen. It's based on a very interesting relationship between the mass of the proton and the mass of the neutron. Protons and neutrons, that's the center of atoms making nuclei. They're almost identical in mass. The neutron is a little bit heavier than the proton, just enough heavier that it can decay to protons together with an electron and an antineutrino. And if that mass difference was just the other way around, then neutrons would be stable, protons would decay. We wouldn't have hydrogen. I talked about this, I call it the miracles of physics. And we think that at the very beginning, before the Big Bang, the universe started in a beautifully symmetric state, and the quarks, particles, all were massless. And then something happened, of course, breaking of that symmetry. It's called spontaneous symmetry breaking. And that made one quark, the down quark, a little heavier than the up quark, and then that makes neutrons decay, that makes protons stable. Anyway, these are what I call miracles of physics. And it could be that it's in our universe that these miracles happen. Other universes, maybe it's different. Anyway, tree of life. So we're all related. We all, according to Darwin's theory of evolution, it took a long time for two cells to stick together and decide that was for a mutual benefit. And then more cells started joining together. But for a long time, we had single-cell life. It's only when two cells more started joining together for their mutual benefit in a way that evolution took off. And so, we're related, if you go back far enough, to plants, smell the roses sort of thing. So they're all, so this is and things branched off there. So Gaia hypothesis, you may have heard about this. It's an idea proposed by James Lovelock. All living things on Earth, call it the biosphere, function as one superior organism that changes its environment to create conditions that best meet its needs, with the ability to self-regulate critical systems needed to sustain life. So this is the idea that all life on Earth, we live in a thin shell, imagine like an egg with a thin shell, that's where all life is. And this hypothesis is that we're all connected, okay? So when we do damage to the Amazon rainforest, we're doing damage to all life and so on. So here I wonder, getting religious about this, whether we have 100,000 millions in our neurons in our brain. When you have hundreds of thousands of millions of living beings, animals, people, and so on, whether they develop some sort of super consciousness that is quite beyond our comprehension, but then actually affecting things. So that's something to think about. Life on other planets. Well, we're finding more and more planets around other stars. I can say how we do that, but here's a very interesting one. 7 planets we found around the star TRAPPIST-1. TRAPPIST was actually the satellite telescope that found it. They're not yet seen, except how do we see them? How do we find planets around other stars? Who saw the eclipse of the sun? Anybody see the total eclipse of the sun? I went to Buffalo to see it. There, the moon completely covers the sun, right? Now, there's also, I think I'll come back. So, now, the planets closest to the sun, Venus and Mercury, when they go around in their orbit, they usually pass above or below. But sometimes they pass right in front of the sun. It's called a transit of Venus or a transit of Mercury. And then you see them as a little tiny black dot moving across. And so if we could have found that had we measured the intensity of the sun and seen this dot coming across by reduction in intensity. That's how we find planets around other stars. We only see them, the star dims when the planet moves in front of the star. Most planets go above or below, or we don't look in the plane of the orbit. But if we're lucky enough to see them going in front of the star and dimming its light by a tiny fraction, 0.1%, we can measure that. And if it happens more than once regularly, we say there must be a planet going in front of the star. And that way we've found thousands. There's another way we find them, which is wobbling. Because as you know, the sun pulls on the Earth by gravity. That's what keeps us in our orbit. Now actually, when we go around once a year, the sun reacts as wobbles also once a year, the same period. Doesn't wobble much because it's much more massive than the Earth. But they have to balance each other. And the other planets too, they go around the sun. And so the sun executing a sort of dance wobbling as the planets go around. And that's, we see, when we look at distant stars, they can now measure stars wobbling backwards and forwards by a very small amount with very sensitive methods of seeing the frequency change. Because when the star's moving towards us, it gets a little bit bluer. Moving away from us a bit redder, the frequency wobbles. And they look at a star, some stars, and they have to be fairly close and bright to us. And some of them they see wobbling, a complicated pattern of movements, only meters per second. I mean, not that fast. But they can analyze this pattern and separate it out into different components. And they find planets around other stars that way. So 2 ways we find them. And okay, so in TRAPPIST-1 they found 7 planets. And this is an artist's picture of what you might see. So some of these planets are in what's called the Goldilocks zone. Not too close to the star, not to be too hot, or not too far away to be too cold. And then in the TRAPPIST-1 system, there are 3 stars, 3 planets that seem to be the right conditions for life. They could have, if they have water, you know, the water would be liquid as well as, and so similar to Earth. We think it may be that to develop life, a planet should have not too hot, not too cold, just right for life, say water. And that's some fraction of the planets that do have. Now, okay, here's another artist's impression of star eyes on TRAPPIST-1d, the 3rd planet. They label these planets B, C, D, E, F, G, and something like that. So here's a familiar habitable zone, sitting around a campfire. You're not too close, you get too hot. You go further away, too cold. So you tend to sit in a ring around that. So this is just a called habitable zone. And so we start to find stars that are in what called the habitable zone. They could have liquid water on, not too hot, not too cold. It's called the Goldilocks. Oh, this is how we can actually maybe detect life on other planets. Not, I think, by listening to radio signals, but by analyzing the atmosphere. So how do we do that? When you have a planet passing in front of the star, well, let me think. When it blocks, okay, the atmosphere of the planet, some light goes through the atmosphere. Here's the thing. Maybe many of you have seen a total eclipse of the moon. You've seen that eclipse of the moon? So you sometimes see the moon looks reddish. Why is it reddish? If you were standing there on the moon, looking back at the sun during a total eclipse of the sun from the moon, that is, the Earth passes in front of the sun, and when the Earth is right in front of the sun, you see a bright red ring, which is sunrise and sunset all around the Earth. That is the light that's come from the sun through the Earth's atmosphere, getting to the moon. That's why it looks reddish. Now, I don't think this has been done yet, but if you were on the moon, looking at the sun during a total eclipse of the moon, so the Earth is completely covering the sun, and we analyzed the light that's getting through, we find lines of hydrogen, nitrogen, oxygen. We could analyze the composition of the Earth from the moon during this total eclipse. That's how we hope, maybe, to find signs of life on a planet around another star. The picture on the left shows a spectrum in the infrared from the James Webb Telescope. And it shows wavelength, and a different function of wavelength, the amount of light, and you see there's structures in there. And this shows 4 peaks due to oxygen vapor in the atmosphere. This is actually a hot gas giant planet called WASP. So when we make progress in measuring we're developing ways of measuring the composition of atmospheres around planets when they pass in front of the star, and starting to find molecules. Now, imagine you're from far away, near a star, you look at the Earth passing in front of the sun, and some of the light comes through the atmosphere of the Earth. They can analyze it. They say, they can say that our atmosphere on Earth is largely nitrogen with oxygen and a bit of trace gases. If they have sophisticated scientific equipment, they can do that. And then our atmosphere is clearly affected by life on Earth. You know, we have carbon dioxide and global climate change and so on. And if we didn't have life on Earth, the atmosphere would have quite a different composition. So I think that in the life of our kids, we will find evidence, or we'll look for evidence, that there's atmospheres around these exoplanets that pass in front of the stars looks lifelike. That is, affected by life, maybe oxygen there and so on. So this is how I think we may first find evidence for life around planets around other stars. And progress is fast, so maybe we'll see it. So, the universe. So, I'm going now to read a poem. I wrote 3 verses poem called A History of the Universe in 3 verses, right? And I can't read it from there, so I have to... Oh, here, thank you. Verse 1. In the beginning was the word bang? Not big, but teeny tiny. 1,000 billion stars inside a grain of sand, even smaller than an atom. They would emerge after 1 billion years with circling planets and later life. Is that how it all began? So here's a sketch of sort of compressed history of the universe. Going time vertically, of course, it's not to scale or anything like that, but the idea is that it started with the Big Bang, which is not really, I say teeny tiny, actually the Big Bang, we see evidence of it when the idea is that the universe started much smaller than a proton, and it expanded and expanded, doubling and doubling in size, until it became about the size of an orange or a soccer ball, and then something happened, called a phase transition. It suddenly stopped expanding so rapidly, continued to expand more slowly, heated up, became very hot, and it's been expanding more ever since, and cooling down, like, you know, when you expand things, they cool down. So now, the temperature of this, the light from that Big Bang, which was not the very beginning, but after this period of rapid growth or inflation, is now down in microwaves. Microwaves you have in your kitchen, the microwave thing. So the space has now got a temperature of about 2 degrees above absolute zero. It's getting colder and colder. And now astronomers discovered that the universe seems to be expanding faster and faster, accelerating into the far future. And we're in a period where, you know, life developed 4 billion years ago or so on our planet anyway. And then it goes into the dark ages in the far future. And I'll maybe come back to my thinking about the dark ages in the far future. But, so here, okay, second verse. Now is the time of our lives. It took 13 billion years, but here we are, 100 billion interconnected neurons in your brain. The plan encoded, DNA in every cell. Ultimate complexity, asking questions, seeking answers. Is that why it all began? Verse 3. But in the end, all life will die. When the last star burns out, extinction everywhere, the party's over, dark energy blows the universe apart. Is consciousness no more? Or is it everywhere? Big bang, then life, then empty end. Is consciousness no more, or is it everywhere? So this is bringing religion into it. But you see, the very beginning, simplicity, complexity comes, simplicity in the far future. So here's what physicists think now, composition of our universe at this time. All the atoms, all the particles and forces we know, is only about 4.6 or so % of all the energy in the universe. So you see, we're ignorant of most of what is in the universe as dark matter, which is about 5 times more than the matter we know, discovered by astronomers who find that things like galaxies are rotating and there's more mass there than we know in the stars and gas and dust. Actually, this was a discovery. Vera Rubin was a woman astronomer who actually nailed that. She didn't get a Nobel Prize. They didn't give it to astronomers and not to many women either. But dark matter is there. We don't know what it's made of. We think it's probably made of particles we haven't yet discovered. It could be very heavy neutrinos or whatever. But then 3/4 of the universe is what's called dark energy. And this is the name given to something mysterious that seems to be like repulsive gravity, that's what's responsible for the accelerated expansion of the universe. And that got a Nobel Prize, I think a bit prematurely, because we don't really know what it is. So astronomers discover this. Cosmologists agree. Probably particles are yet to be discovered. Maybe too heavy or too light, too weakly interacting. So now you may have heard of the Higgs boson. There's a book called the God particle. So what is this? What is it called a God particle? Actually, I was privileged to be part of the team that discovered the Higgs boson at CERN, and also the heaviest quark we know. That's the quarks. On the bottom right, you see a diagram of all the particles and forces that we know in the matter part of the universe. But why did they call the God particle? So cynically you say, well, it sells books, which is true. Leon Lederman, who I knew, he was director of Fermilab, he said, well, the publisher insisted. But he went along with it, okay. Most physicists, it's a quantum of a field that fills the universe. And it's got no direction, it's the same everywhere. So we're familiar with gravity, the field that keeps us down on the Earth, and ball comes back down. Gravity is what Einstein says is a shape of space and time, but we're familiar with that. It varies everywhere, and it's got a direction. Electromagnetism also varies everywhere, magnets and so on. You feel them, the force, which is different from here to there, and it's got a direction as well. But this Higgs field is a so-called another field that has no direction, it's just got a value, and it's the same everywhere through space. And it gives particles the mass. So if the Higgs field, which has a value, if you turn that value down to 0, particles would lose their mass. Electrons would have no mass, they'd travel at the speed of light. And also, the forces, the different forces, we have the weak force responsible for radioactive decay. And that is covered by a exchange particle called W and Z bosons. They would have no mass if the Higgs field was turned down. That was, the physicists thought, how come an electron here in your little finger, an electron in the Andromeda galaxy, they have the same mass? And you can actually make them out of light. You can collide two photons, which have no mass, just energy, and make a pair of electrons. You can do that here. I've done it here at Fermilab, actually, and another galaxy, and it come the same. They come out of the vacuum, and they've got a certain mass. And if they didn't have that mass, we wouldn't have atoms, because electrons would have no mass. They'd speed off at the speed of light. No atoms. So this is why it was called the God particle. But here's all the particles of the standard model of physics. You see, we've got 6 types of quark in orange. The U and D stands for up and down. They make up protons and neutrons. Below them you see E and neutrino. So up and down make protons and neutrons when they're stuck together. The electron goes round and makes atoms. The neutrino, there are 3 types of them, and they have interesting, strange properties. The other quarks at the top are charm and strange and top and bottom. They're all unstable, and they decay down in a cascade. Anyway, and on the right you see the force particles, Z, or Z, W, and gamma and G. So gamma is the particle of the electromagnetic force, Z and W of the weak force, G of the strong force. Anyway, so here's a bit of a busy slide about the Higgs boson. So Professor Higgs and others said that a potential usually called, I have to read it here. Usually, I should wear my glasses. Hang on, I've got glasses here. I can read it. Then I can read it over there. All right. So that's why we electrons and so on have the same mass, and they know what mass to have. How do we define the vacuum anyway, if not the absence of any stuff? Let's say it's the lowest potential energy. So the vacuum, it's got this Higgs field in it. It's got also dark energy. Professor Heisenberg, okay, never mind about that, but by the way, next year is the 100th anniversary of Heisenberg's quantum mechanics. So it's the year of the quantum next year. That was in 1925. And he said that energy and time are like reciprocals of each other. Energy and time are related. Energy is like the inverse of time. And that was a brilliant idea, actually. And now there's another busy slide a bit about dark energy. What is it? A ubiquitous, extremely low density component of the vacuum. Anyway, Hubble found the universe was expanding, the accelerated expansion. Einstein, when he was thinking about the universe, thought it was static. He had his equations, and actually his equations said it should be either expanding or contracting, but not stable. He thought it was stable. He didn't know about Hubble's discovery. He put a term in his equations to make it stable. And then he found out that Hubble had found that the galaxies are moving away. He said, damn, that was his mistake. He could have predicted that. But he put in this term, and then later we found that the universe is actually accelerating its expansion. And so then it's brought back the idea of this dark energy or the vacuum having a repulsive power. At the bottom you see again this pie chart of the universe, and there's a graph that shows the possible ways in which the universe is going to expand in the future. It could blow up, getting faster and faster exponentially forever. I don't believe that actually, but or it could collapse down to a big crunch in the future, and then there's this Goldilocks principle again. Bit of detail there. Oh, I'm sorry, it's a very busy slide, but you can forget about it if you like. But it's a graph on a logarithmic scale of time. The top line, far left. At the left you see an equation up at the top there, which is an equation that Planck put together from 3 fundamental constants: speed of light, c, Heisenberg's constant, which relates energy and time, and the gravitational constant of Newton, which is the strength of gravity. You can put those 3 numbers together in a way that you get out a distance and a time and a mass. And the distance you get, the time you get is 10 to the minus 40 seconds. And then that's on the far left. I haven't got the laser pointer. The far right is the age of the universe, and we're right in the middle. So there's a timeline from the very beginning, and I think that the universe started way before the Big Bang. The Planck size, was a bit of like a fluctuation in some outer space-time that I don't understand. That was so perfectly symmetrical in space and time. And then what's called symmetry breaking occurred, giving rise to the different forces and masses of particles. And that could be different in each universe. And the far future is, again, can be that the universe becomes very simple again. So anyway, this is a complicated slide, so let me come further. But here's the famous Ouroboros, the snake biting its tail. Okay, so it's interesting now that particle physicists who look down to smaller and smaller things, smaller than a proton, we find quarks, and then so is that the end? Is the quarks the smallest particles? Probably, I think so. Below that level is symmetries. But then the astronomers look out into the universe, they rewind the clock, and they say that the whole universe was smaller than a proton once. So we look down very small, look very big. Physics is, and then, so this is like a diagram of space, but it could be time as well. Round to the top, on the left side, going down and down to smallest things, down to the Planck scale. Humans are down in the middle here. It's a logarithmic sort of scale thing. And round to the right, bigger and bigger and bigger, the whole universe. And now you're seeing the smallest things and biggest things are somehow connected. It's a circle. And this has been an ancient religious thing. Well, I took it out, but the idea of the snake biting its tail goes back into prehistory, and it's used in a religious symbol. And I think that this is actually a sort of image of the universe. So here's a model of the universe as a closed loop. And I gave a talk about this at a physics conference in California 2 weeks ago. So it's based on three principles. The first principle is called the CPT theorem. And all theorists believe this is absolutely a symmetrical thing. C stands for charge, but actually it's matter-antimatter. So positive C is matter, negative C antimatter. There should be, obviously we're all made of matter. Where's the antimatter? But it had two principles. One principle is that there are no boundaries to space-time. I'll show a bit more about that. That is, space, like the surface of the Earth, two-dimensional surface. It's got no boundaries, no edge. You can sail around the Earth, but it's finite. It's not infinitely big. It may look infinitely big if you look at a small part and see it's flat, but you go out further, you see it's actually curved and closed, two-dimensional surface. Now, I say if space-time, not just space, but time. I mean, Einstein unified space and time. So time also is finite with no boundaries. Has no boundaries. The third principle, there's no infinities in the physical world. Infinity is mathematics. Maths is full of infinities, very interesting things. But I suggest, by hypothesis, if there's nothing in the physical world is infinite, no infinite space, no infinite time, and no infinite things mean no singularities. The singularity is a zero. It's the inverse of infinity. So if some people think that the Big Bang started with a singularity, is zero size, I say no. This principle forbids infinities and singularities. So the universe started then, not with zero size, but the size of the Planck scale, which I showed you before. And then how does that work together? So here's a sort of cartoon of the universe with space and time having no boundaries but both finite. So it's hard to see what this is, but think of a torus, a ring like a rubber ring, okay. Now, that has got two radii. One is around the small part, the other is around the big part, right? Now, the one in the small part represents one dimension of space, and the round big part is time. So they're both closed. It's a toroidal topology. Now, we know the universe is expanding, so the space is getting bigger and bigger. So you have to constrict that torus to a very small, not zero, but very small size at the beginning. And then in the far future, it has to come back together, which means that time is not infinite future, not infinite past either. It becomes a closed loop. Now, in this diagram, I can only show, I've shown so time goes around the loop. Starts a Big Bang at the very far left, which was a Planck scale size in my idea. And it's deep time on the far right, when the universe has expanded so much, it's so dilute, there's like 1 electron per cubic light year, and then the other side. So look at this at the left at the Big Bang. It's got an upward branch and a downward branch. The upward branch is where all the matter is, our universe. The downward branch is where the antimatter is, because it's totally symmetrical between matter and antimatter. Now, in the very far future, how can they join together? Do you have teacups and anti-teacups joining together? That wouldn't work. So, in order for this to work, all complexity has to have died away. Protons have to decay. They decay to an electron and photons to conserve charge. The electron is there. In the other side, in the antimatter part of the universe, which is disjoint from us, the antimatter particles have to decay away. So then in the very far future, so the top branch, I call it matter, the bottom branch is antimatter, and in the far future, it doesn't matter. They come together, and now you have electrons and positrons all coming together. Now, Feynman said you can think of a positron like an electron going backwards in time, and that fits in with this picture. So one viewpoint is that the beginning of the Big Bang, a anti-universe pair creation happened. They separated, and now there is a distinct, separated in some outer dimension, outer space-time, if you like. But in the far future, after all complexity has died away, it becomes simple again, and that sets a time scale for this. Because protons seem stable, but we think they're complex. They've got quarks and gluons inside, like neutrons do. Neutrons decay, that gives a direction of time. But that means that the far future, when they come together, has to be longer than the lifetime of the proton, which we know is more than 10 to the 30 years. How do we know that? Well, you get 10 to the 31 protons together, and you see how many decay in a year, and that's looking for that. We haven't seen proton decay yet, so we put a limit. They live at least 10 to the 30 years. But if this idea is correct, they have to die away in more than 10 to the 30 years. So that sets a scale for the time of the universe. Now, what about the time of our lives when entropy is growing? Here, entropy has all died away because entropy is about complexity. So, here's the thing. You mix, you put milk in your tea and it becomes milky tea. It doesn't go back the other way. Time is going one directional. But the CPT theorem says that for particles, time is forward backward symmetric. So the time of our lives, the time of our memories, psychological time, entropy time, is only transient. It started when complexity came into the universe, which is around the Big Bang time, but not at the very beginning. And it will have gone away by the time matter's all decayed. Protons are decayed, stars are decayed. You've only got only a universe full of electrons and photons. So that's that. And so that says that's our universe, model for our universe. And in my thinking, it's in some sort of outer space-time, an extra dimension, if you like, where the anti-universe now is separate from us, only connected to us at the Big Bang and in the far future. Right now, it's there. It could be almost no distance away, actually, parallel to us. And this is an idea that theorists are working on, that you have a membrane like... Anyway, but if there's one, that doesn't make any more sense than the one planet, one Earth, We now have 100,000 million planets, 100,000 million galaxies in our universe. So why not 100,000 million universes? All separate, all distinct. No connection by physical means, that is the particles of light and so on between them. So in some outer space-time, if you like. And that is a version of the multiverse. And this could also be without any boundaries. It could be like a toroid, but none of that had to be expanding or contracting because there's no gravitational interaction between these universes. So it could be static, and then this is a sort of toroidal topology of what I call totality, where there's 100,000 million or 100 billion or trillions of universes popping into existence. And they all may have the perfect symmetries that we had right at the very beginning of our universe. But the symmetries will break differently in all of them. It's a random thing that happens called spontaneous symmetry breaking. So all these different universes would have different masses for their particles, different forces. And it so happens that we're in the lucky ones because we've got, stable matter, we've got hydrogen. But maybe in vast number of these universes, they didn't get lucky and there's no life in them. That's becoming very theosophical and so on. But ours is just right. Goldilocks universe. People talk Goldilocks principle planets, some are just right for life. I'm saying with vast number of universes, some are just right for life. This is the Ouroboros. It got out of sync here because my computer died at 9 o'clock this morning. So this is the first, on the left, the first known image of an Ouroboros, a snake biting its tail from a tomb of Tutankhamun. On the right, you see a medieval map from alchemists, again, the snake biting its tail. And I'm saying that the universe, the far future, the far past, they come back together. So, the vacuum. Well, okay, I can skip this, but I gave a colloquium about the physics of the vacuum, and okay, so I'm near the end now because the Unitarian Church, and so on joining the church, I went to a course that was 25 years ago. Build your own theology. Okay, think about what do you think about God, and so on. And so, build your own theology. Now, the ancient peoples, the sun, a powerful thing, affected us, the moon, stars, earth. These are all things they didn't understand. They didn't have the scientific knowledge to understand it. So they were gods, sun god, moon god. Now science has explained these in terms of particles and forces. But the things we don't understand. Universe, totality, all life on Earth, are we all connected? This Gaia idea, we're all connected life on Earth. And our subconscious, where our emotions and feelings and love and so on, these are not things, in my view, that are part of the standard model of particles and forces. But, so these three, if you like, is my trinity, the universe, all life on Earth, and our subconscious. We don't understand those, so for me, they're manifestations of God somehow. And then invisible energy, the dark energy. So physicists don't understand that. That is something that you can say, well, I've got ideas about that, but you can say that is connected to complexity, connected to our subconscious. When you have an intuition, you don't know what to do, you do something, then it's coming in from your subconscious. And then we're connected. You go to I was at a symphony orchestra, National Symphony Orchestra, everybody's there listening to wonderful music. We're all connected somehow. You have a peace rally. And this is, I think, bright energy, or a religious revival or something like that. Then you have what I call dark energy, which is where you have, like in the 30s, a Nazi rally with Hitler ranting and raving, and everybody feeling this dark energy and getting dark. And then, so for me, the dark energy astronomers talk about is one end of the scale. Another end of the scale is, this is my personal religion, if you like. But invisible energy can be dark or bright. It's a scale. And the bright side is what I call God. The dark side is what I call devil. And I don't know if everybody realizes it, God and good, same word with just one letter missing. Devil and evil, one word with one letter missing. This is true in English. I don't know if it's true in other languages. So yesterday I picked up this book in my free take-a-book library. All I really need to know, I watch Star Trek, and I've got a couple of quotes from this. It's not good, but it's entertaining, about Star Trek. Spacecraft zipping around at many times the speed of light, violates the laws of physics that link matter with mass, the speeds of matter less than the speed of light, but relating space and time. So that's why I don't believe that rocket ships can come, even at faster speed of light anywhere. But maybe invisible energy is not limited by the speed of light. What's good, another good quote from Star Trek, or at least Dave Mariant, who wrote the book: each person or each species, no matter how alien, has the right to live their lives as they wish, as long as they're not trying to take over the galaxy or eat you or something. That's also a lesson from Star Trek. I'll skip this because it's complicated, but it's a diagram that relates space and time, energy, momentum. It's my STEM diagram. STEM, you know what STEM means. I call it space, time, energy, momentum. Space and time are related by the speed of light, c. Energy and time are related by Heisenberg's constant h bar. And energy, momentum, also gravity. So I've got STEM, and the three constants of nature there, c, g, and h bar, are making Planck space and time. You put them together, you make Planck. And anyway, this is, I think, a very concise diagram. How conservation of energy was realized by Emmy Noether, a mathematician. She said, if the laws of physics don't change with time, energy has to be conserved. And if the laws of physics don't change with space, momentum has to be conserved. So these are relationships between that. And so anyway, thank you. That's time for questions. Thank you. Yes? Yes. Okay. This is, I had a slide to show this, but take a look. Are you anybody wearing a wedding ring? Okay. Go around the ring. So think of it as a one-dimensional line. A line is a mathematical concept, a one-dimensional thing. In mathematics, it's got no width. A real physical line has got a width, but in mathematics, it's got no width. But you can turn it into a loop, and now you've got a line, one-dimensional line with no boundaries, but it's finite. Now, think of then a surface of a sphere, like the Earth, but a perfect sphere is also finite, but no boundaries, no edge to it. That's mathematics again. Now, Einstein eventually developed a theory. Well, mathematicians in the 19th century said three-dimensional space can also be finite with no boundaries. Sounds weird, we can't easily picture it, but that's mathematically possible. And how you think of it, if the universe was like that, static, finite, no boundaries, you shoot a light beam up there, you go as straight as you can, you'll eventually come around back where you started. You've gone all around the universe. Hard to get your head around, but there's mathematics. Einstein said, maybe the physical universe is like that too. Finite with no boundaries, three-dimensional space. And I'm saying, well, maybe, and interestingly, Einstein said that about space. He didn't say that about time. Time was supposed to be infinite past, infinite future. I'm saying, well, maybe time is also closed like that, and that's a whole other story. But that's how space can be finite with no boundaries, the universe. Now, we know that the universe is expanding, it's not static, okay? And it's expanding faster and faster, so practically we can't send a light beam off in this direction and get it coming around the other way. But that's because the universe is expanding. If the universe was contracting, it would start to be, you start to be able to do that.
Isn't that a similar sort of shape to torus that you talked about?
Yeah.
Maybe there's another shape?
Could be. Could be. This is the simplest one, I think, because, in Einstein's theory of relativity, he unified space and time. But time is not another fourth dimension of space. Time is different from the three-dimensional space. We've got three-dimensional left, right, up, down, forward, back with three-dimensional space. You can say where you are with three dimensions. Einstein said, I think 4 dimensions, we've got a point in space, x, y, z, and time t. But time is not a simple fourth dimension. In his equations, he puts in front of t, IC, where c is the speed of light, and I is the imaginary, making a number complex. So I is like, so this is like, already to that equation, it says time is somehow orthogonal to space. And that makes this topology seem natural. That you have time as it's orthogonal in the same way that around a torus, where one coordinate, that's only one coordinate of space. Now you have to go to 3 coordinates of space, and then 1 of time. So it's like our universe is expanding, 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 and in this idea, it has to be, the expansion has to slow down, stop, and the same thing's happening in the anti-universe, and they come together. So time is a closed loop. So, food for thought. Yes, Bob.
I'm going to throw a curveball at you, and that is, if light climbs to this extreme where, the universe and the anti-universe meet, isn't it true that you climb the gravitational field to the point that all light and lost all of its energy? It's like trying to climb out of a black hole. The light doesn't quite make it because the gravitation stretches it to the point of oblivion and loses all its energy. So the light that's at that extreme, I would think, would be stretched to the
Right.
point of no energy.
Yeah. Yes, no, that's right, because as the universe expands, the wavelengths of light get stretched and stretched and stretched. Light photons lose their energy. So in the far future, the energy is down to almost zero. I say not absolutely zero, because zero is 1 over infinity, but practically zero. And also, I thought, how can an electron in our universe match a positron in the other universe? And they match, well, you can't think of them as particles now, they're waves. And the electron wavelength is light years. And so then the waves come together, and this relates to the particle wave duality idea.
I mean, at the point, at that extreme point, where you have no motion, it's not, the identity of particles and antiparticles almost disappears because it's an arbitrary.
Well, yeah. But if you believe that, as I do, that electric charge is conserved, it doesn't disappear. So in the far future of our universe, protons have decayed. The universe is just a very dilute plasma of electrons and photons. Physicists think protons may decay. Grand unified theories say protons would decay. And the lifetime of the proton is more than 10 to the 30 years. When they decay, the end product is an electron, conserved charge, well, a positron in the case of a proton, and photons. But the wavelengths of these photons and the wavelength of the electron, which is also a wave, is now vast. And Feynman said, we can think of a positron as an electron going backwards in time. And that, but it's, or it can be the other way around, But in the far future, you've got this, now, according to this idea, the dark energy causing the expansion of the universe, it has to stop expanding because that would be infinite future and no infinity. So it has to stop expanding.
So one other final curveball. If you have all these positrons decaying protons, and you have the electrons that are particles and atoms, then those guys wouldn't they annihilate in space and time?
They do. They come together. It's not in the case of annihilation. If you think of one electron in our universe.
I mean in our universe.
Yeah.
In our version, if a proton decays into a proton and like,
But, yeah.
and maybe if you have a positron and a proton is conserved in charge, and you have an electron, so that the universe is still neutral charge. Even in our universe, before you get to the extreme, you have positrons and electrons. Those guys start annihilating right both the house.
Right. Okay. No, that's a good, interesting point, actually. So in our universe, I mean, think of the stable matter, protons and electrons, okay, neutrons. So the protons will eventually decay to a positron to conserve charge. And for every electron, there's going to be a positron. So from proton decay, because the charge has to be zero. So in our far future, when the protons are decayed, it's now a vast plasma of positrons and electrons. The same thing in the anti-universe. And they come together, and you don't have to think of the electron as a point-like thing matching a point-like thing, because they're now waves. And They're waves when they don't interact with anything, which they won't in the far future. They're particles when they interact with something. So, when you see the wave particle business, when you see a track of a particle in a bubble chamber, string of bubbles, right? Every bubble is made by an electron ionizing an atom, and that seeds a bubble. That ionization event it's a whole other story, but it's a growth of entropy. It's a one-way thing. It doesn't happen backwards. And that's when it's a particle. In between, when it's not interacting with anything, it's a wave. So like young slits, you have a light source, you've got slits, you've got a detector. The light source is when the photon is interacting, and that's a particle. Detection, it's a particle. In between, it's a wave. When it's not interacting with anything, it's a wave. So that's one idea.